Hello, everyone. Joining us today is the Vice President of Princeton Satellite Systems and Deputy Chair of the Nuclear and Future Flight Propulsion Committee for the American Institute of Aeronautics and Astronautics, Stephanie Thomas. How are you?
Hey, Brennan. I'm great today. As I said, it's cold and rainy outside, but it's a great day to be inside and thinking about fusion.
Yeah, the news cycle has been a bit of buzz about all the fusion energy talk, and we wanted to take the opportunity to ask you a few questions and get your take on it. So let's jump right in.
You bet.
Can you recap in your own words what's been achieved at the Lawrence Livermore National Laboratory and what's meant by the term scientific energy break-even? It's kind of been thrown around a lot here.
Yeah, I was tossing this around with my colleagues a little bit. But so break even means that you have, two opposing quantities, like one positive, one negative, that are equal or at least equal. Like if you have a garage sale and you make as much as you spent on your signs and advertising, you broke even, or any sort of financial little shop or store. So for energy break even, we're talking about we're putting some energy into a plasma and then it's doing fusion and we're getting energy out, and we're getting out at least as much as it took to put in. So the break even would be, zero. The amount in equals the amount out. So, right, for the reaction to achieve break even means that it produced energy at least as much as it took to heat and confine the plasma. So this had actually never been achieved in a fusion experiment before. This was the first time. And the National Ignition Facility uses lasers to induce fusion. And so they had energy break even in a single shot on December 5th. So just 10 days ago. And they actually did better than break even. They produced 3 megajoules of energy from 2 megajoules of laser energy. So they actually achieved a science gain of 1.5. So we have to use the caveat that this is scientific break even or science gain, because it doesn't account for the total amount of energy it took to make the laser energy or the laser pulse. So as a matter of fact, those lasers required 300 megajoules of energy to make the 2 megajoules that went to the plasma, or we'll say the wall plug power was 300 megajoules. So when we account for that energy or the engineering gain, it was actually less than 1%, because the lasers are very inefficient. But even so, it's the first time that we can definitively say, that the fusion produced energy.
So this is very significant. It's never been done before. And as you were saying, the scientific proof is, it's on the way to, something closer to economically viable. And so you were kind of starting to describe it there, but what's the main difference between that scientific proof of principle and how does that vary from the engineering proof of principle? Can you dive into that just a little bit more and sort of the differences there?
Yeah, and we think about this a lot when we're thinking about our own fusion plant design. So they showed with the laser pulse that it's possible to deliver energy to the plasma and get more energy out, which is, of course, a necessary first step to using fusion as an energy source. We have to get more energy out. But this is equivalent to, say, burning gasoline for the very first time in a lab on the way to building a car engine. We don't have the engine yet. We just have, a little spark. So in order to get from here to the engineering proof of principle, which we would call a prototype power reactor or a pilot plant, we have to build the rest of the engine. So we call this the balance of plant. So you need all the equipment that's going to actually make the electricity, or in space, the propulsion from the fusion energy. And you need all of the equipment that it took to create the plasma heating and confinement, which for the National Ignition Facility, they have a bank of 192 lasers that's as big as 3 football fields to make that pulse. So you have to have all of that balance of plant, and your fusion energy has to make more than all of that takes. So now, it's the whole thing. So the wall plug power or the engineering. So that's what we mean when we say net gain. It's not just the power we actually managed to get into the plasma, but the total amount of power it took to run and to maintain it, right? So if you need control power, to keep it going. So, and then just for an example, so tokamaks are the donut-shaped confinement reactor that we have here in New Jersey at the Princeton Plasma Physics Lab and NSTX, or with ITER in France. They all need a science gain of something like 20 or 30 in order to have, the net gain for electricity of, I'm going to say 5, but you need a lot more science gain to get an engineering gain.
So it sounds like they had a gain of 1.5. And while this is really significant, really what you want to see is something like 20 or 30 before it's economically economically viable.
And again, they've been working on this, I think, since 2009. And, and they've shown it, right? They've shown they can focus the lasers, they can focus them on the pellet, and they can actually, produce energy from the energy that went into the pellet. So again, it's an important step, but, it took 300 times that energy to make the lasers are especially inefficient. So you'll see some articles about the news are saying that, they think that while the laser, it's an important milestone that the magnetic confinement fusion might be the first to make an economical plant or might beat lasers because the lasers themselves are so inefficient. And again, in order to have a power plant, you have to make electricity. In the end, the goal is to make electricity. So you have to have net power. So I did have another comment I wanted to make about the fuel that they used. So they were using deuterium tritium fuel, which again is the easiest to burn because you need the lowest temperature. So again, that's great for the science proof of principle. We're showing we can make fusion work at all. We're showing that yes, it can, release energy when we get it to start. But the engineering proof of principle that you asked about also has to include breeding the tritium in the case of those fuels. Remember, tritium is a radioactive isotope. The half-life's only 12 years, so it decays pretty quickly. It's extremely rare in nature. So in order to have a power plant that's using it, they have to breed it inside lithium in a blanket inside the plant. Okay, so if it's engineering proof of principle has to have that blanket, it has to make its own tritium. That's a whole additional subsystem that has to be developed, the science and then the engineering to get to your net wall plug gain. And I also wanted to mention that the neutrons from that deuterium tritium reaction are also very destructive. So again, in a science experiment where they're only running, one shot a day, and so they're not producing that much radiation, but for a power plant, it's going to be running, constantly or every minute, pulse, pulse, pulse. So for your engineering proof of principle, you have to have the materials that can withstand that neutron bombardment. So then there's those big gaps are also with the fuel and with the neutron bombardment between the science and a working plant.
So to summarize, it's one great step, but there's still a lot of different things to work out in terms of getting to that net neutral, even net gain overall. And let's use that to sort of transition into what Princeton Satellite Systems is doing, and how is the fusion that you're doing different from the lasers, so to speak? I think you touched on it by saying it's electromagnetically bound, but dive into that a little bit more.
Yeah, so the PFRC, right, the Princeton FRC, which is field reverse configuration, our design uses magnets to confine the plasma and then radio frequency antenna to heat it. So it's closer to a tokamak than it is to the laser fusion at the National Ignition Facility. However, it has some important differences from a tokamak, which is because it's that field reverse configuration or a little plasma ball, it uses its magnets more efficiently than tokamaks do. It has a higher beta. So we actually don't need as high a science gain for net electricity production. So it simplifies some things. The PFRC will be designed for steady state operation. You turn it on and it stays on rather than pulses. So that laser fusion, I talked about, they did one shot on one day with the fuel pellet. Pulsed fusion plants, when it pulses, that's a lot of stress on all the components, right? Because then you have, all of your energy is compressed into a shorter amount of time. So that can have more stresses on the walls and the components. So a steady state reactor like we're hoping to build relieves some of that strain on some of your subsystems. So that's one of the things that should make it easier to operate and develop. It reduces the instantaneous loads on all of the equipment. We also plan to use deuterium helium-3 rather than deuterium fusion. And that comes back to the fact that our FRC plasma, this plasma ball, is a more efficient use of magnetic field, so we can get higher temperatures. So instead of planning to burn deuterium tritium, which creates all these neutrons, doesn't exist in nature easily, you have to breed it, we're planning to use helium-3. Helium-3 does exist. It's not radioactive, so once you have some, it's not going to go away. It exists on the moon. It exists in the gas giants. We can breed it on the ground if we need to, but it doesn't produce those neutrons in the primary reaction. So it really reduces the engineering difficulties. So once we have a science proof of principle with our PFRC, it should be much easier to go to that engineering proof of principle because of our fuels, because of how efficiently we use our magnets. We don't need as strong magnets. It's like an MRI machine, which you may have seen at the hospital. That's sort of the size and scale of the magnets. So it's smaller and simpler.
Sounds like, there's a lot of differences, but you have a clear path to proof of principle on that engineering side that, has a little bit of a lower bar than those lasers that are can be pretty inefficient. But it seems like, there's a lot of work to do, to make fusion energy become more prevalent. And so what are some milestones that you're looking forward to at PSS that contributes towards that effort of fusion net gain?
Yeah, well, I was going to say that it's great that teams all across the world are working on different fusion concepts, from the laser concepts to the tokamaks to the stellarators to FRCs, which other big commercial companies are working on different types of FRCs, including pulsed FRCs, because we don't know yet what's going to make the best power plant. Now, we're looking specifically to make a small portable machine because we are excited about its applications in space, but because our heating method is relatively new, so our milestones that we're focused on in the short term are demonstrating our heating method, achieving certain plasma temperatures, building a stronger machine, probably more than a couple generations of stronger machine with stronger magnetic fields, still only the size of an MRI machine, but stronger than the experiment we have now, to demonstrate that our heating method is as efficient as we think it will be. So those are our short-term milestones. But, as a community, we have a lot to learn about what it takes to control fusing plasma. I also wanted to point out, that there are other FRC and mirror concepts, again, under development. Maryland has centrifugally stabilized system. Wisconsin's working on a mirror. Helion and Trialpha are working on FRCs. So when we make progress in an area, like, it benefits those teams. When those teams make benefits on stability or fueling, like, we can learn from them. So there's a lot of synergies across the groups. So even though our machine is a lot smaller than they're hoping to build, we can still, it's a community, and our science helps each other. So we're still all contributing to the greater knowledge of, making fusion stable and controllable and workable.
Yeah, even though this is, a really tough problem, it sounds like, everyone's kind of competing, but at the end of the day, knowledge is shared across the community and we're all working towards like the same goal here. Does that sound about right?
Yeah, and I had an analogy I came up with, which I mentioned back, when they first discovered they could make gas from oil and they burned gas. They were still a long way from a car, right? And over the years, right, since the 1905 Model T, how much more efficient have car engines gotten? And there's all kinds of engines, right? So your lawnmower has one kind of engine. There might be a two-stroke engine, a four-stroke engine, car engines, diesel generators, and they all work on the basis of combustion. So fusion power is not just going to be like one single type of power plant, but potentially a whole range of fusion powered devices in the future that we can't necessarily conceive of, how they might be used, how small we'll be able to get it. Will we achieve, we were talking about Mr. Fusion from Back to the Future, who was only like a coffee can. But I do foresee, again, different styles of power plants, different types of fusion devices having different applications.
And now the biggest notion out there from sort of the detractors to fusion, it's always 20 years away.
Yeah.
And that's the prevailing narrative in the media. What can you tell folks listening to convince them that we'll actually get there?
Well, I like to sort of use your phone as an example and think about how much power and computational power, how much technology is in this phone. And when my dad likes to tell my son about the first computers that he worked on, when he was in college or when he was at his company, and his first computer had no hard drive. And then they had an entire room full of these cubic yard modules, and that was like 20K of memory, right? And now we have this. And it's because of these kinds of technological advances in computation that we're now able to learn things about plasma and design heating methods to get the results that you're seeing, right? So the reason the NIF was able to have success with this pulse was because of technologies like machine learning. And they used machine learning specifically to find the fuel pellets that had the least defects that were most likely to get the most power out in their pulse. Technologies like better power electronics. I was also going to make an analogy with your electric car. So, right, again, some of the very first cars, when they were developing cars over 100 years ago now, they were actually electric, but they couldn't get enough power density in the batteries. And now the reason our electric cars are having this great range and are so wonderful is power electronics and semiconductors and new semiconductor materials that are much more efficient. That's coming back and making the lasers work better and the various power electronics that are used to heat the plasmas and control the plasmas. So all the technology that is ubiquitous and we're getting used to is also making things like fusion closer to reality. So again, it's computation, it's technology, it's materials, superconductors. Like, think of the giant wind turbines that they're building now from, the wooden windmills that you would see in the Netherlands. And they're remarkable technology. And again, all those wonderful rare earth magnets, all the technology is like in the giant wind turbines. So, or to bring it together, like technology is going to make us solve this problem. And they achieve net gain. So all those times when there's Reddit threads or there's a press release and you see all the negative people like, well, but no fusion has ever achieved net gain, like how can we talk about commercializing something that's never worked? Well, now I can say, guess what, somebody did show net gain, and they were able to design something that could do that. So
It's
I
kind of
have
like, a rising tide raises all boats, or whatever that analogy is. The technology that's not necessarily, directly related to fusion, but it's all sort of moving together. And fusion is one of those technologies that will also progress along with it.
and it's benefiting from all of this other technology now that we use every day, like AI, right? You use your phone and you talk to Siri, and there's these new AI that you can demonstrate, or I talk to Alexa, and that's all AI, and they're using AI and machine learning in fusion to find which of the hundreds of parameters they should tweak to get more efficient fusion pulse. TriAlpha used it with a collaboration with Google. So again, these technologies that we're immersed in every day are the same technologies that scientists are using to advance fields like plasma physics and fusion. So it's all related.
Sounds like we'll get there, and you're confident.
This is it seems like it's been a long time to get to this point, but if you actually plot how we're doing in fusion on triple product or temperatures, you can see it's going up, and it's been going up continuously, and now we've crossed this important threshold with showing net science gain for the first time. So yeah, it should be only forwards from here.
Well, that's exciting. And, we can do a little bit of dreaming about what can come with fusion once it is, commercially viable. And I'll ask you to do a little bit here. But other than propulsion, which I know you guys are excited there at Princeton Satellite Systems, what application of fusion are you most looking forward to once it's become commercially viable?
Yes. So, again, we are hoping to, in the end, solve climate change. Again, with helium-3 for us, it's a little more challenging because we also need a source of helium-3 in order for grid scale power. But one application that you and I talked about was vertical farming. And this is where instead of, having to use all of our farmland, you create basically a skyscraper and you grow all your plants hydroponically. And I've seen lectures where they think they can grow pretty much anything, strawberries, blueberries, fruit trees in this vertical farm. So you can produce the food right where people consume it, right? And save all of that transportation energy, more efficient. But the power, because now you're pumping water and you have to provide all the light for the plants. So everything that was happening in nature, you're replicating in the building. And I saw this lecture and they were talking about all these wonderful things, but that it's going to, instead of farming the area of Kansas, you need solar panels the size of Kansas to power the urban farming. And I thought, I know what would work a lot better in those buildings, and that's your small modular fusion reactor. So, and for example, data centers, right? Data centers are also something that's really power hungry. Again, and when I'm calling Siri on my phone isn't actually doing that, right? At some giant data center that's sucking electricity in the grid somewhere else is actually doing that calculation. So our needs for power are only going to grow. And yeah, I would like to eat strawberries that were vertically farmed without pesticides and were fusion powered.
Yeah, I think we'd all love to go inside of that skyscraper and just walk around for a little bit with plants, up to the sky, and every type of vegetable you could want in one building. That sounds like a pretty utopian future to me.
Yeah, and it independent of seasons, independent of flooding, right? You could let all the rivers go back and be for fish because you'd be growing all of your food in your urban skyscrapers. So you can restore a lot of environment if you have something as power dense as fusion, right? It's about freeing the environment from all of those constraints of having to carpet it with either fertilizer or solar panels.
Yeah, fusion has many applications that can make the future bright, and I think that's the excitement that everyone's feeling around the news cycle this time around.
Yeah. I got so many texts and messages from neighbors and friends like, hey, I saw this in the news. So yeah, I got in touch with a lot of people because of that excitement, and I'm glad that people are excited about it and paying attention. It's important.
Well, Stephanie, I want to thank you for joining us today. Is there anything else you'd like to say to the Space Ventures viewers here before we sign off?
I would just like people to, stay interested and stay forward thinking. And, it is a little science fiction come true, but, just all the technology that we're experiencing every day, fusion is going to come along for the ride.
Awesome. Well, thanks again.